The Royal Swedish Academy of Sciences has decided to award the 2017 Nobel Prize in Chemistry jointly to Jacques Dubochet, Joachim Frank, and Richard Henderson. And the Academy citation runs, for developing cryo-electron microscopy for the high-resolution structure determination of biomolecules in solution. Für die Entwicklung der Kryo-Elektronenmikroskopie für die hochauflösende Strukturbestimmung von Biomolekülen in Lösung. Pour développement de la cryomicroscopie électronique pour la détermination haute résolution de la structure des biomolécules en solution. За развитие крioelektronной микроскопии высокого разрешения для определения структуры биомолекул в растворе. And you see pictures of our Nobel laureates on the screen above me. Jacques Dubochet was born in 1942 in Switzerland. He studied in Basel and in Geneva, and he is currently honorary professor at the Université de Lausanne in Switzerland. He's a Swiss citizen. Joachim Frank was born in 1940 in Germany. He got his PhD at the Technical University in Munich, München, and he's currently professor at Columbia University in New York. He is nowadays a US citizen. And last but not least, Richard Henderson was born in 1945 in Scotland. He received his PhD at the University of Cambridge in the United Kingdom, and he is since many years at the Laboratory of Molecular Biology in Cambridge. And I think he is the 15th Nobel laureate from that laboratory. Rather impressive. With that, I'll give the word to the chairman of the Nobel Committee, Sara Snogerup-Lindsö. She'll provide a brief summary of the research that's been awarded today. Sara, please.
Thank you, Göran. We are made of more water than anything else. Biomolecules, the molecules of life, they do their job in water. So let's put them there. Now they are free to move and act and interact and do their job together to help us execute important functions like thinking and carrying around stuff. Every protein in here is roughly 10 nanometers in diameter. So if I were to reverse this process and pull out 1 million of them and put them along one line, they would cover just a centimeter. Cryo-EM is able to see each and every one of these protein molecules, and it can do much better than so. It can see each and every atom inside each protein to tell us how they are arranged to build up their intricate structures. It can do even better than so. It can show us how the different parts of the protein moves relative to one another when they execute their jobs. Richard Henderson showed the first protein structure at atomic resolution using cryo-electron microscopy. Jacques Dubochet developed a method to take these samples of biomolecules in water and freeze them so rapidly that they formed a thin film in which the water was preserved in a liquid state, just like in a glass window. Joachim Frank developed a method to combine the information from multiple blurry images of those individual proteins into one sharp image. Soon there are no more secrets. Now we can see the intricate details of the biomolecules in every corner of our cells, in every drop of our body fluids. We can understand how they are built and how they act and how they work together in large communities. We are facing a revolution in biochemistry.
Thank you, Sara, for that great introduction. Now, Peter, can you show us perhaps what those molecules in the glass look like?
I'll try.
Thanks.
So this picture shows three examples of structures that have been determined using the technique that has been developed by the laureate. And the first one on the left side is a biological clock. It's a protein complex which controls the time in many living organisms. And this is closely related to the prize for physiology or medicine that we could hear about a couple of days ago. In the middle, it's a pressure sensor, or it's of the type that is used, for example, in our ear to convert the sound waves into electrical signals. On the right side, it's a huge protein complex that is used by Salmonella bacteria to inject harmful substances into the host. This is the host and this is the bacterium itself. And these structures have been determined using the techniques developed by the laureates, which have opened up a completely new world to us to be able to see all these molecules inside the cell and how they interact. The challenge is that these molecules are very small. The size relation of a molecule like the one I showed to a human being is approximately the same as of a human being to the size of the moon. We currently don't have any instrument that would allow us to see a human being on the moon from the surface of our planet. But we do have an instrument which allows us now to see the molecules inside our cells. And not even that, we can even see the atoms that build up these molecules and see the details of all these molecules. The electron microscope is not a new instrument. It was developed almost 100 years ago. The problem is that there is a great challenge in studying biological objects using electron microscopy because there must be vacuum inside the electron microscope. And biological objects are composed primarily of water. And if you place an object containing water in a vacuum, it dries and the structure changes. If you switched on the electron beam then, the object is burned and the structure does not even remind us about the original object. Richard Henderson studied an organism or a protein from an organism that lives in salt ponds like the one shown here in the desert. This is a microorganism which carries patches of photosynthetic proteins on its surface. And these proteins, they are arranged in regular arrays that contain many, many of these molecules. And Richard Henderson placed these patches in the electron microscope, and by observing about 5 million of these bacteriorhodopsin molecules at the same time, he could distribute the electron radiation over a large number of molecules so that each one of them did not receive enough electron radiation that would damage them, but he could then study the molecules. And in this way, he could obtain a high-resolution structure of the protein of bacteriorhodopsin. But this is a special case. Not all molecules are oriented like in this case, in this microorganism. Most molecules are free or like Sarah showed in water. And Richard Henderson believed that the technique could be also used to study essentially any molecule that is found in the cell. When we study a picture of molecules that are in solution, and this is an example of a ribosome that we see in solution here, all the molecules are randomly distributed in the solution. So they are difficult to find. So the challenge is now using this very low electron radiation that would not damage the molecules to actually see them and see where they are. Then we have to see how are they oriented relative to each other, because we must know in order to determine the three-dimensional structure to combine all these pictures into the whole structure. Joachim Frank developed these methods, and it's illustrated in this schematic illustration. So here are the molecules in solution. They have different orientation. When these molecules are illuminated by the electron beam, we see projections of these molecules, like shadows of these molecules. And these shadows differ in shape depending on the orientation of the object that was illuminated. This can be now sorted. Those that have the same shape or originate from molecules with the same orientation are sorted in groups. And then an average of all these pictures can be taken in each of these groups. And in this way, one can obtain sharper pictures. One can increase the signal relative to the background noise. And this is the way now to obtain better resolution pictures. Then these pictures can be combined to build a three-dimensional structure. And this is an example of such a structure. But in order now to obtain information about the details, about the atoms, what the molecule looks like inside, better sample preparation methods were needed. And many people believed that the way to prepare samples would be to freeze them. The problem is that if you place a biological object in ice, in water and freeze, then ice crystals are formed around the object. And the ice crystals diffract the electron beam. So when it's illuminated, all the information is lost because the ice crystal diffract the electron beam. But people also believe that it would be possible perhaps to freeze the sample fast enough so that the water would not have time to arrange itself into crystals to form ice, but would be a structure that is like a liquid. All the water molecules are randomly distributed and not forming the ice crystals. And if this is the case, then it would be possible to obtain a sharp picture because all the electron beams would be evenly absorbed by the vitrified water, as it's called. And in this way, Jacques Dubochet could develop the technique that allowed to see biomolecules at good contrast. The method is described in this picture. So the sample is applied to a grid, and the sample then in water spans the distance across the holes in this grid, and then the sample is frozen in ethane that is cooled by liquid nitrogen. So the temperature is about minus 190 degrees. It's rapidly frozen, and then the glass is formed. The water in the glass form is formed across these holes. This is a setup that was built by Jacques Dubochet, and we see here it's like a catapult that is used to inject the sample that is here into the cold ethane here. So it's frozen very rapidly in order to form this vitrified state. And using this method, Jacques Dubochet in the beginning of 1980, he showed these beautiful pictures, like in this case of a virus. And everyone who were working in this field traveled to his lab in order to learn the technique, and it was then rapidly used in many other laboratories. The technique has transformed the electron microscopy from a technique that could be used to just see the shapes, the outer shapes of molecules, into one that is now used to see the details, the atoms inside the molecules. And the latest technical developments occurred very recently. So it's very recent developments that we can actually see the details of these molecules. The technique is also relatively rapid, so once one has samples that can be studied, the structure can be determined relatively rapidly, and this was exemplified last year when the structure of the Zika virus was determined in just a few months, and it's seen here. And this structure shows the atomic details of the surface, which of course is important when developing drugs against the virus. But the technique is not only about seeing molecules, and I think this is fantastic for developments that has already started, but will be seen also in the future. And that is because the molecules are frozen in solution. If a molecule does some work like the one shown here, then all these molecules are frozen exactly in a moment, in the different states, in different structures, and it's like frames of a movie. Each of these pictures represents a frame, and they can be put together into a movie like the one shown here, and we can see what the molecules do. So I think in the future, this is not only about getting structures of molecules, which are in itself, it's of course fantastic, but it's also for the future, we'll be able to see processes, what is happening, what is going on inside the cells, how do the molecules interact, how do they move, what do they do. And I end this presentation by showing the laureates again. Thank you.
Thank you, Peter, for that beautiful and exciting presentation. Now, I hope we have Professor Joachim Frank with us on the phone. Dr. Frank, are you there?
Hello? Here?
Yes, hello. And thanks for being with us. This is Göran Hansen, who I believe woke you up an hour ago or so.
Didn't mind.
Good. Now I'm in the session hall of the Academy, and we have journalists from Sweden and all over the world here. And I'm sure they have questions to ask you. Who would like to start? Thomas von Heine, as usual, please.
Good morning, Professor. This is Swedish television. Congratulations.
Thank you very much.
We just heard something about the usefulness of your technique or technology. Could you, in your words, what would be the main usefulness of it?
Well, structural research has been mainly done with X-ray crystallography for the past decades, and X-ray crystallography requires molecules to be arranged very rigidly in crystals, so it's not applicable to all molecules. So molecules go through many different states, and not all these states can be captured by X-ray crystallography. So the cryo-electron microscopy of single particles fills an important gap. It extends the range of molecules that can be determined at atomic resolution, and it also makes it possible to see these molecules in the functional states that are relevant for the life functions.
Do you see any immediate practical use? I think that's an interest for our journalists here.
Well, the practical use is immense, but there's always a long time between the results of fundamental research to make their way into the general knowledge and the practice of medicine. And you might know that the X-ray crystallography during the past maybe 5 decades has resulted in 100,000 structures that are all publicly available, and they now form the fundaments of molecular medicine. Medicine is no longer looking at organs. It looks really at the processes in the cell, and that's how medicine has become so powerful. And the same transformation will happen with all the results that are gained by cryo-electron microscopy. It is just not an immediate bedside application, but several years to go by before the practical use is seen.
Yeah, exactly. We have a question over there from the lady over there.
Hi, I'm Annelie Megner-Arn from Swedish TV4. Congratulations. I wonder which one is the coolest molecule you have seen through your microscope?
Well, for me, I've been looking at ribosomes for a big part of my life, and for me, the coolest molecule is always in the ribosome. So the recent revolution that has been produced by the development of the very sensitive cameras has resulted now in dimensional images of the ribosome that are incredible in terms of understanding the function. we can now see how the ribosome can distinguish between the correct and the incorrect pairing of an anticoder, meaning the decoding, the essential process that takes place in the ribosome cannot be explained in atomic detail.
Let me we have some slight problems with the connection, so I'll just mention the ribosome, the machinery that makes proteins in the cell, is the most remarkable structure for Dr. Frank himself. And you can see even the details when the amino acids are put together now. So that's what's thrilling for Dr. Frank. We have one more question over there.
Yes, we were told at the press conference that the Zika virus was analyzed using your method. Could you please elaborate a little bit about that specific application? Were you involved in that at all?
I was not involved in this. This was done by Michael Rossmann at Purdue University, and actually the reconstruction of viruses have a great advantage over the reconstruction of molecules without symmetry, because a single view gives you, in the case of this particular symmetry, it gives you 60 views, and so you have many more information just from a single view. The methods that I developed were not so important for the development of for the reconstruction of the virus.
But they were a start of something very important, weren't they? We have a question over here.
Thank you. David Keaton from the Associated Press. A question in two parts, if I may. First of all, sir, how did you react? What was the first impression when you received the phone call this morning announcing this prize? And the second part is, over the last few days, the Nobel Prizes that we have heard that have been announced, the importance of the technological innovation and breakthrough was stressed several times. The importance of that technological breakthrough that enabled these scientific discoveries. Do you believe that in this era today in scientific research that the technology is sort of paramount and actually maybe the first step before the actual fundamental science discoveries?
Okay.
Well, as to the first question, I was fully overwhelmed. I thought the chances of getting a Nobel Prize are minuscule because there are so many other innovations and discoveries that happen almost every day. So yeah, I was in a way speechless and only said this is wonderful news, and I repeated myself. And as to the second question, I think the Nobel Committee or the Nobel committees always have this they have this quandary of deciding whether fundamental breakthrough is worth the prize or a technological innovation. Technological innovations, in mind, have much larger impact. Cryo-electron microscopy is about to completely transform structural biology, and which can be seen from the fact that crystallographers flock to the conferences in cryo-EM, and there are also many applications by postdocs for postdoc position of students that have been trained in X-ray crystallography. So I do think that deciding between a particular discovery and a technological breakthrough, I would always think that the impact is probably much larger for the technological breakthrough.
Okay, thank you very much. I think we'll have to stop there, and thank you very much for being with us, Professor Frank, and we look forward to welcoming you to Stockholm in December. Thank you very much, and bye-bye.
I very much look forward to that. Yeah.
Now are the questions for the panel. Yes, please. Axel.
Yeah, thank you. I'm Sufjan Axel Song from freelance for China Radio. So far, we have 9 laureates, and about 7 is from the USA. So I just like to ask you to have a comment about this. How do you comment the research environment or policies in the US, or why it's like this? Yeah, thank you.
Well, if I'll start, and maybe my colleagues can expand. The United States has, since after the Second World War, allowed scientists to perform fundamental research, to focus on important questions in science, not forcing them to immediate applications, not controlling them in a political way. And that freedom, combined with very good resources, have been very helpful for the United States. But it's not unique to the United States. As I mentioned, Richard Henderson is at the MRC Laboratory of Molecular Biology, the LMB, in Cambridge, UK, that has fostered a whole long list of Nobel laureates because of the intellectual atmosphere, because of resources for basic research that has turned out to pay off in practical applications later on, but they are not pushing them to try to solve immediate practical problems, but to lay the foundation for that. And I think that has been very helpful. In other parts of the world, of course, they have been less privileged. The situation has been very different. We've had colonialism, we've had wars and so on. It's been very difficult to mobilize enough resources for science, but it's also a matter of the intellectual climate allowed in the universities. Sara, would you like perhaps to add on that?
What I could add, I mean, of course, the academic freedom, I think, is the key to making big discoveries. But what we can do as Nobel committees is that we invite universities and individual scientists from all over the world to nominate. That's how we work to get in nominations from the whole world.
That's an important point. We really give opportunities to scientists on every continent and in most countries to nominate. We make some efforts to give that opportunity. Yeah. More questions? Please. Gentleman over there.
Yes, it's Yiming Fu from China's National Xinhua News Agency. It seems to me that this year's discovery is a combination of physics and chemistry. You know, we're talking about microscopy, light and imaging, as well as the molecule structures. So can you tell us how important it is for this interdisciplinary methods in research of chemistry in future? Thank you.
Peter, would you like to comment on that?
I think it's a very good example of how contacts between scientists in different disciplines is, and I think it's the discipline, the development is such that the discipline mix more and more, I think. And as you correctly pointed out, I mean, this is a particular good example where both technical developments and methods, mathematical tools have been developed, and also preparation techniques. So I think this works together, the different disciplines, different backgrounds of scientists work together to develop techniques like in this example.
Thank you. More questions? If not, then we'll close this part of the press conference, and those of you who have requested interviews, you will have that opportunity in a minute or so. Thank you very much.
Så, tack.
Jag frågar igen vad du heter.
Johan.
Du är Nobel member. Vill du eller ska jag?
Peter Brzezinski, this prize is about seeing the invisible. Can you tell us something more about this cryo-EM, cryo-electron microscope?
I think in a way it's a revolution because now it's possible to extract molecules from the cell that are in the same environment as they're usually in the cell, in the water, and also see the structures of these molecules, but also see how they interact with each other, how they operate. One can get, since all the particles, the molecules that are studied are in a solution, they are frozen in the different states, and one can then combine the different pictures to understand function as well, dynamics. And that's the sort of key to understanding life.
Everybody knows what the microscope is, but how does this one look like?
It's a big box that is, I think, 3-4 times taller than we are, and then there is a chamber where one places the sample, and then it's illuminated inside. There's vacuum inside. It's cooled, and then there's a camera, which is one of the key components, I should say the key components developed most recently. That is used then to detect the pictures and monitor the
So it's like big, like a room.
It needs a whole room, yeah, and it must be very stable. The floor must be stable because it's sensitive to vibrations and so on. So it's a big, expensive machine.
Do you have one?
There is one in Stockholm, which is shared between Stockholm University and other universities and at SciLife Lab. And then there is one in Umeå also.
And do you use it?
Yes, we do use it. We just started recently because the instrument is new, but we do use it in my research also. I think a lot of people are really interested in using the instrument because it can provide so much information that is it's very important for understanding function.
So what would be your dream discovery with this one?
I think for the future, I mean, first of all, it's to see the molecules we work on. I mean, that's in itself, it's something very rewarding to be able to see the objects you work on. But I think for the future, and which is now more and more become possible, is to observe, as I mentioned before, these different states that one can freeze the sample, freeze the molecules, why they do something, to actually combine the information into a movie or to understand the dynamics, how they interact, what they do, what happens inside the cell. I mean, this is with purified proteins, of course, but one can then try to understand what happens inside the cell as well.
So are there any more secrets that are not revealed in the living cell anymore?
Not yet, because the technique or the status is relatively new. So the possibilities to use this technique in this way that is used today has only been possible since just a couple of years. So I think now it's an explosion in research, and what is limiting now is access to the microscope actually. So the waiting time is very long. So I think with new microscopes and more microscopes, I think there's a lot to be seen.
It was also a very long way to develop this one. It's like since 70s or 80s. What was the main obstacle that you would pick up?
I think from the beginning, the problem was that studies of biological objects in an electron microscope, it's not trivial, because there is vacuum inside, which biological samples contain primarily water, so they dry inside and shape changes, and the pictures are useless. Then the electron beam burns the molecules, which also changes the structure even more dramatically. And this has been a challenge to be able to reduce the intensity of electrons, of the radiation, and yet be able to see something in the background noise. And this required both techniques for developing the microscope, the technology itself, but also techniques to be able to find the molecules in the pictures, because since one has to reduce the radiation, the light in equivalent to light in a light microscope, but here electrons, and then the pictures are very weak, so one has to find where the objects are. One has to see how they are related to each other in space, and this requires mathematical methods, mathematical tools, and computer programs. And there's, of course, the sample preparation to be able to freeze the samples in such a way that the picture is not distorted. So research has been going on very actively during a long time, but there has been a lot to do before the technique matured into the state it's today.
Not to kill the life in the cell.
Exactly,
yes.
exactly. No, kill the molecules even.
Yes. There is this very special way of freezing the water, the solution, that you call
it's called vitrified waters. Yes, yes. So the idea is that normally when one freezes water, ice crystals are formed, and ice crystals diffract electrons so that the information is lost, because the electrons are diffracted always. So the idea was to freeze the water so fast that the crystals would not have time to form. So, and this is called vitrified water, like a glass. It's the same principle as a glass in a window. It's also a liquid. All the molecules are disordered and they are not crystallized, but it's like a liquid that is like a solid, but it's actually on windows. You can see in the lower part of all old houses, the windows are a little bit thicker. And it's the same way here.
Transparent.
Yes, right. And it's the same way here. Freeze water so rapidly that the crystals don't have time to be formed, and it's like a uniform glass that is transparent, or actually it does interact with electrons, but in a uniform way. And this allowed a technique to be developed such that contrast could be increased, and one could see the molecules in the pictures in the electron microscope.
I understand. So now you have a perfect instrument, or would you like to modify it a little more?
I think there's more to do. I think the new detectors, which was the latest breakthrough, they are not perfect. There's still a lot to do to improve them. Also, the sample preparation methods could be improved. The way the cryo stage and where they are kept, and the temperature is kept constant because variation in the temperature can cause movement. So there are a lot of techniques, and also, I mean, it's in principle very little sample is needed for the studies, but since one has to apply a droplet to this grid, one has to remove almost all the sample, and very, very small fractions, like a droplet in a bathtub that is actually left. So if one could develop techniques that would allow applying very small amounts of sample, then there is, of course, many more molecules that could be studied, because it's not possible to purify all molecules at an amount that allows studies. So there are a lot of pieces that can be improved, and I think for the future it will. I think the technique has a lot of promise. Yeah.
And my last question, perhaps, what did the laureates say when they got the call from Stockholm?
But from what we had some problems with the telephone line, but those that I heard were very happy and surprised, and we're looking forward to coming to Stockholm in December.
Thank you very much.
Thank you.
Thank you for taking your time with us.
Thank you.